Alright, I think we can get started now. So today we're going to be working on Daedalus, which is my programming language that compiles to a Turing machine. And today the stream is going to be broken up into two sections. In the first part we're going to be talking about how exactly the program works, and a little bit about what a Turing machine is, if anyone's unfamiliar. And the second half is going to be hopefully devoted to working on a couple of things that I'd like to get done pretty soon here. So this is the main file here, and this is the main section, and right now we have a lot of hard-coded things, the tape of the Turing machine, and the optimization level. And what I'd like to do today, after I go through the explanation of the program, is make it so that this tape can be read in via a file, and a lot of these options are done in the command line. So first, I'd like to start off with a simple explanation of what a Turing machine is. I'm not going to go into too much detail. It's kind of below the scope of what the stream is today. But I'd just like to go over it really quickly in case anyone is not familiar with it. So a Turing machine is a computational model, which is just a fancy phrase for it's a theoretical way of being able to compute things. And a Turing machine has a few things. It has an alphabet, which is just its list of symbols that it's going to be using. So this is usually 0 and 1. And one of these symbols is considered the blank symbol, which is usually considered the first symbol in the alphabet. And the blank symbol is special because it's the only symbol that appears on the tape infinitely. And the tape is essentially an infinite list of symbols. And you can think of it like the RAM of the Turing machine. So it'll be just a lot of zeros. And, there can be a few ones in there, which is going to be the main data of the Turing machine. But mostly, it's going to be just zeros infinitely in either direction of the tape. And then there's the head, which is kind of the current address of the Turing machine. And so it's going to be pointing towards a very specific symbol, and it will move left and right as it needs to read in the various symbols. The head has obviously a position, and it also has a state, which is just a number that kind of decides what set of logic to use going forward. So it can move over here, and it can change state, say 13, and move right. So it's just a way of addressing which state to use. And the states have a table, and they're composed of three things. They're composed of the write, the move, and the next state instructions. So whenever a Turing machine gets to wherever it is trying to go, it will first write a value, depending on which one it reads in. It'll then move a certain direction, usually right or left. There is some variants that have no movement, but they are not considered a traditional Turing machine. So we have right, and that's just a symbol from an alphabet. Move, which is just right and left. And the next state tells you which state we're going to be transitioning to. So for example, let's say we had a state 0, which is usually just the initial state that you start out in. And we are at this position, and we're at state 0. We're going to be reading in a 1 instead of a 0. So let's say if we read in a 0, we want to write back that 0 move left, and then go to state 23. However, if we read a 1 instead, let's write back that 1, move right instead, and then go to state 14. And so this is one single state. For each symbol in the alphabet, there is a single column that describes exactly what we're going to write, what we're going to move, and which state we're going to next. And so this is those instructions for if we read in 0, and this is the instructions for if we read in 1. And so just using this basic set of instructions on what a Turing machine is, we can actually compute all things that a computer can compute. So that's the basics of what a Turing machine is. So now the question is, how do we build up a programming language that can directly be interpreted as a Turing machine? Well, we can start off with what are the basics of what a Turing machine does. So we already established that it does a write, it does a move, and then goes to another state. In addition to that, some people like to introduce the idea of an acceptance state and a rejection state. And the basics of this is eventually the Turing machine has to stop or halt. And this offers two ways of doing it. The accept state, if the Turing machine ends in that state, means that the input was formatted correctly and the Turing machine ran properly. If instead it ended in the reject state, that means that either the input was not formatted correctly or the Turing machine's logic failed and it reached an error state. And then on top of that, if we first off change the next state to go to, as that's more appropriate for a programming language, we see that while this is indeed what a Turing machine does, it's all deterministic. If I'm writing, moving, going to, accepting and rejecting, there's no if, there's no branching. It's all just going to run down the program line and be very definite. So we need to introduce some sort of branching or otherwise testing logic into it. And we can do that through the use of an if goto. And the way that this works is when the Turing machine reads in the symbol, if it reads in a specific symbol, it'll go to a given line. And it turns out that just with these 6 instructions, we can actually have the entire span of what Turing machines are capable of doing. And so if we look at the actual language now, we see that it's very similar to what I've described here. So here we have the alphabet of the Turing machine. We have a label indicating start, and we'll go into labels a little bit later. And we have if, go to, move, go to, reject, accept, everything that we talked about here. And this is the actual intermediate language of the programming language right now. Eventually, I plan on separating the two so that there is a much higher level language with variables and while loops, much better control flow, things like that. But for right now, I'm just working on the intermediate language and getting it set up. So, with that in mind, how exactly is this code interpreted? How do we go from this to a Turing machine? And there's really 3 ways of doing it, and the 2 are kind of specializations of the others. The first way that we can think about this is if we take just one line and think about what the Turing machine logic is behind it. If we read 1, go to found num. Or in our case, let's just make it easy on ourselves and say, go to state 2. So we start in state 0. We don't know what we're going to do if we read in a 0, so we'll leave those blank for now. And we know that if we read a 1, we're going to be going to 2. So we want to write back that 1 because there's no instruction to write here. We're going to move right just arbitrarily. And then we're going to go to state 1. And then state 1, no matter if we read a 0 or a 1, we want it to write back what it's reading, because now it's in a different spot. We don't want to change any values. We're going to move left to counteract the right here. And then we're going to go to state 2 as instructed. And so we see that if this is run on a Turing machine, and we just have a 1 symbol, we can see that it'll move right, it'll write back that 1, then move right, which will introduce a 0 here, because that's our blank symbol, and then it'll write back that 0, move left, and then go to state 2. And so by still moving and still doing all the instructions that a Turing machine normally does, we've created an equivalent relationship between this notion of if we read in a symbol, go to a certain line of code, and a Turing machine. And so we do this similarly for every line. Move is very simple. It's just one state, write back the symbol you read, and go to the next state, making sure you move right. And so we can go through all of these states, or rather all of these lines of code, and write an equivalent set of states that matches the logic perfectly. So this is the naive way of doing it, and it's good. It gives you kind of a one-to-one relationship here where one line of code directly corresponds to a set of states, state 0, state 1, and so on and so forth. And while this is very useful, especially if you're debugging this code, it's not very useful for generating concise programs. Turing machines aren't very fast in the first place, and interpreting even basic logic as a Turing machine can result in a lot of states. And so in order to minimize the number of useless logic states and just having a lot of states in general, we have to introduce some sort of optimization. And that's what I have here in this file, is all the logic that goes into optimizing. It's a lot right now. It needs to be rewritten and refactored. But the basic part of it is we need to recognize, first of all, that not every combination of lines of code can be compressed. For example, move right and then if 0 go to concat. We can't combine that into a single state because there's two reads here. For one thing, there's one read when we decide to move right, and then there's another read when we decide whether or not we're going to branch here. So in order to actually combine these two states, we would have to have two reads in a single state, which is not really possible. Or otherwise have two reads in two states, but we find that that's also not possible because this if 0 go to needs two states itself. So we end up with three states no matter if we combine these two lines together or not. So we have to interpret them as separate. And so that's what this logic here does. It just goes through the current list of instructions that it's reading down and decides whether or not it can be optimized. And if it can't, then it goes down to this function here, which actually returns the optimized state. So there are some situations where we can combine the logic of a few states. For example, this is a very, very common pattern in Turing machine logic, and by extension in this language. If symbol, go to line of code, move right, and go to start. Now the implied logic here... Ooh, sorry about that. Now the implied logic here is that if we are reading a 1, we're going to be going to found num. And if it's a 0, we're going to be doing these instructions. And so we can actually combine all three of these lines together into a single state. So we know that if it's a 0, there's no write instruction, so we're going to write back that 0. We're going to move right, and then go to start. And that's if we read a 0. And then if it's a 1, we want to write back that 1. We want to move right, and then go to found num. And so now we've taken 3 lines of this code and compressed it down into, well, actually this should be to a temp state, and then temp will return you back to where you started. Left, left, and found num, found num. So we've taken 3 lines and we've compressed it down to 2 states, where normally this would have taken 5 states, 2 for the if go to, 1 for the move right, and 2 for the go to. And so using just that very basic idea, we can actually combine multiple lines of code into a single, or rather a couple Turing machine states. And so that's what this very large function does, is just interprets the current set of instructions and returns the optimized set of states out of it. So that's all well and good, and we can get very good results just by applying that optimization, but even with that logic, we still end up short of optimal. And that's a problem, especially when we're considering that we're going to be having another layer of abstraction on top of this. If we have something that's storing variables, we're going to have logic in the intermediate language that is determining all the logic and control of that variable. And so it's not hard to see that we'll end up with a lot of states just for something as simple as a variable declaration. So we need to do better in our optimization. We need to be as close to perfect as we possibly can while still maintaining the structure. And this third level of optimization is a little more complicated to follow through with, but I'll go through it as best I can. The important thing to recognize here is that the first 2 optimization states that I talked about are good for debugging. Remember before we had one single line of code will correspond to a set of states. And then in the second optimization, we have a set of lines. So, if go to, move, and then go to will itself correspond to a set of states. However, to get past this, we have to completely leave behind individual lines, and we have to start thinking just in the logic of Turing machines. And this is called look-ahead optimization, and that's done by this function down here. And there's 3 main parts to this optimization. The first is what's just pure look-ahead. So let's say we have a state that is if you read 0, move right, and go to state 3, let's say. Or if you read a 1, go right and go to state 1. And then state 1 will look like write back your symbol, move left, and then go to state 2. And then state 2 will be something like if you read a 0, write a 1. If a 1, write a 0. move right or left, and then go to state, say, 4. And this is a pretty common pattern that we see here. This is, if you remember, just the if go to expanded into 2 states. Now the problem with this is that if we look at how this is actually going to be run on the Turing machine, we see that while we're here, we're going to write back the 1, move right, and go to state 1. And then it produces a 0 here. And then when we're at state 1, all it's going to do is write back whatever we read here, move left, and go to state 2. We've changed nothing, ended up exactly where we are, but we're using a different set of logic, which is this one here. So it would be much easier if we just took the logic from here and just completely cut out the middleman. No need for any movement. Just immediately do what we're going to be doing in the future, which is why it's called look-ahead optimization. And this has many advantages. The first of which being that we have potentially eliminated the need for state 1. If nothing else references it other than state 0, then why keep it around? And that changes this to state 1 now. And it changes these values as well. And on top of that, it may also have eliminated all references to the new state 1, which was originally state 2. So we could potentially get rid of that. And so just by looking ahead and closing these loops of logic that we have, you'll see that we can actually eliminate a lot of states very easily. In addition to this, by changing the logic of this state, we open ourselves up to the opportunity of having multiple states that are equivalent. So let's say we have another state down the line, state 15, for example, that has the exact same logic as state 0. And this does happen from time to time. You have a loop that meets up in 2 different places, but just the way that you have been writing the code, you didn't recognize that the logic was the same. Well, if these 2 states are the same, anything that references state 15, let's say state 16, we can just change these references to state 0 because it's the same logic. And this potentially can allow us to remove state 15 altogether. And now this becomes state 15. And that's carried out by this logic here, where it condenses the repeated states. And then changing all the references, because this was originally state 16, but we got rid of 15, so this had to become 15. That's handled by this section here. And then finally, by changing all of these references, we have also opened ourselves up to a final, very powerful optimization. And that is, some states will end up not being referenced at all, especially if there was originally a duplicate state. And so we can just completely eliminate those. And that's what this code takes care of here, is it just goes through and eliminates all the unreferenced states. And it does it multiple times, as many loops as it needs to do through the code to find all unreferenced states, because sometimes you can have loops. So for example, if we had a state 5 that referenced state 6, and then state 6 was not referenced, or rather not referenced, we can eliminate state 5, and then all of a sudden state 6 might not be referenced. So we need to run through the loop multiple times to find all the ones that are not referenced. So those are the basics of how the optimization works, and this actually gives very good results. And let's go through a little bit of that now. So this is a program that writes, or rather that performs unary addition on a Turing machine. That is, if we have a tape that reads 11101111, in unary this is interpreted as 3 and 2. And so the sum of those would obviously be 5. And so the result that this Turing machine gives is it gives us 5 in unary, which is like this. And so this is just the logic of that written in the intermediate language. Oh, and the intermediate language is called WB1. So if we look at the logic, the first thing that we need to do is we need to interpret it in a more concise way. That is to say, it's not enough that it looks like code, it needs to act like code. And so here we have it kind of lexed into a more consistent format, and things can easily be read in without having to worry about did they spell go to right and such. And so this is kind of what the intermediate language will actually end up being, is just these symbols. And then the actual Turing machine that we end up with is one second. The actual Turing machine that we end up with is like this. And this is unoptimized. And you can see that we have, just like before, here's state 0, here's state 1, state 2, and so on and so forth. And so it's actually taking this logic and turning it into the Turing machine. Now, what does this look like with optimization? It's very drastically different. Let's see. Here's the optimized version of the same program. And you see it reduces it down to only 5 states. So we went from 29 states to 5 states. And that is actually optimal for this problem. It's impossible to do unary addition with less states. So for this specific example, our optimization is actually perfect. And that's actually the case for all the ones that I tried out so far. Obviously, it's not able to return completely optimal Turing machines for a given problem. But for your logic, it's as optimal as it can get, really. So, close this here. So right now, this is just the intermediate language, as I said. It will eventually become more of a robust language with variables and all that. For now, let's see here. For now, we're just going to be working on the section I mentioned before, where I want to be able to read in the initial tapes as a text file, rather than having it just be hard-coded into the program, as it is now. And being able to have multiple options for when you run the program. So, for example, if you wanted to just lex a WB1 file, as this function does here, you could do that. Or if you just wanted to run a Turing machine file by loading it and then stepping through it, you can do that. So first thing we're going to do is work on reading in just the text file for the machine tape. And if anyone has any questions at any point, go ahead and ask. I'll be monitoring the chats as I go along. So first thing we're going to do is just get rid of the tape altogether. And if we go down the line here, we find that after we load in the file path, we're going to want to load in the tape. And if we go into the Turing machine definition over here, we're actually going to need the header file as well. We're going to add a function to load in that text file. And it's just going to be a plain text file. The other files, like the Daedalus main file, is .ddls. Obviously, WB1 is .wb1, and the Turing machine file is .tm. I just want the tapes to be plain text, just to keep it as simple as possible. There's no reason that a tape should be interpreted as anything other than plain text. So if we go down here, we're going to add in another function, and theoretically, there's no real way for loading in the tape to fail, but there might be, we might do like symbol checking in here. I'm not entirely sure. So let's see, int load tape, and it's just going to take in the standard string file path. Okay, and then in the main file, we can write that function. Loading tape, and then taking the file path. Right, so the first thing that we're going to want to do is create the IF stream. We're not going to be writing to this file, so it's sufficient to just be a file in. And then we are, I like to set the standard iOS bad bit, because sometimes when you are manually writing files, the null terminator at the end of the file doesn't quite get interpreted correctly. Sometimes you have the end of the file just be a /n with a 0, and then when you go to read that line, it just reads in the /n, and it can cause some problems when you're reading a file line by line, like I like to do. Okay, and then I'm going to actually open the file. I'm just copying this, it's the exact same thing. And we're going to create a custom directory for this, which is just going to be stored in the tape section. And we're going to actually open the file, and we're going to create a variable to read in the line. So first off, we have to check if the file is even open in the first place. And if it is, that's going to be our main logic there. Otherwise, we need to throw an error. So just standard cout, error failed to open file. Okay, so now if the file did open correctly, we're going to read in the line, which is standard get line, and that'll be the line, and let's see, oh sorry, got that backwards. That'll be the file and the line. And the format for the tape is just going to be a single line, I think. That'll keep it as easy as possible. These aren't really meant to be human readable, other than obviously a Daedalus file. These are meant to be auto-generated files, or very quickly typed up files. Like a tape file might be, it takes a couple seconds to write in 1110111. So these don't really need to be human readable, and there's really no reason that a tape would be so massive and you would have to read it in. So it's sufficient that it's just a single line. So now we're going to actually read in the symbols from the line. And the way that I want it formatted is exactly as I typed it there. just characters separated by a space. Now, in the Turing machine definition, the symbols are just simple chars. So we could theoretically just have them next to each other like that. But while I did say that the files aren't really human readable, I do like to have things spaced out. I do find it's easier to just to get things easy to read, because otherwise a bunch of ones and zeros, it just, your mind kind of glazes over a lot of the information there, and it's hard to catch errors. So we're going to be just iterating over the line. So just set up a simple for loop. C less than line dot, not line dot end, line dot size rather. And then machine tape, we're just going to push back the symbols as we read them in. And actually, instead of plus plus c, we need to do c plus equals 2, because we have a space in between them. So we have tape.pushback line at c. Now at this point we could introduce a logic to check whether or not the symbol that's being read in is in the alphabet. And the reason I don't want to do that just yet is, I forgot to return -1 here. The reason I don't want to do that just yet is I can imagine a situation in which you have a Turing machine and you haven't yet set the alphabet, but you still read in the line anyways, and so it's trying to find symbols in a blank alphabet. I just like to keep it as flexible as possible, and obviously this will throw an error as it tries to simulate it if it finds a symbol that it's not able to identify. So I think this will be fine for now, but eventually we'll have to decide whether or not, I'm going to put a little to do, we're going to have to decide whether or not we do symbol check. So this will fill the tape of the machine with what it's reading in from the line, and then after it does that, we can just close the file, close, and then return 0. So now, let's try and create a sample tape for one of the programs. Currently, I have it loaded with a source that I added last night, which was the unary multiplication. And so we're just going to add in if machine.load tape. And for now, we're just going to hard code this as init tape.text equals 0. And then it'll run the actual Turing machine. So let me go ahead and add that initial file here, and I'll show you. Okay, and we called it init tape.text. So let me go ahead and add that in. Okay, so this is for our unary multiplication file. So whatever numbers we put in, it's gonna multiply. So we'll just put in something simple like 110 111. So this is 3 and 2. And it's going to multiply them together to get 6. That's the expected result. So let me save this. And I already have the command line set up in my project settings so that it'll read in the appropriate file name and everything, so it'll read in the unary multiplication automatically. So let's go ahead and step into here and take a look at what happens. Oh, I just compiled that and released, sorry. One second. Switch that to debug. Okay, so everything else ran fine, and now we're at the load tape function. We're going to step into that. And it looks like it did find the file. Now it's going to read in that line, and we can see that the line is exactly what we typed in before, just 111011. And now it's going to iterate across that, and let's take a look at line at C and at tape. So we're reading the first one, and accordingly it pushes it back on the tape, and this will repeat, and we can see the tape is now 111011 as we expected. And it closes the file, returns 0, and now it will actually run the tape. So if we skip running the tape, and we take a look at machine.tape, we can see that it gives us 1, 2, 3, 4, 5, 6, as we expected, a result of 6 from multiplying 3 and 2. So everything ran perfectly. Okay, and just like that, we have now a method of writing an arbitrary tape onto here and reading it in. So if we now change this to say 3 times 4, and we expect we expect 12 as the result, we can go ahead and skip to the end and get rid of this breakpoint. And indeed, on the tape, we see, starting from 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So everything runs perfectly. So that was easy enough. So from here, I'd like to add more functionality to the command line. And to do that, we need to really think. Didn't mean to click that. We need to really think about what exactly the program does right now. And that is, it can compile a Daedalus file to a WB1. It can then compile WB1 to TM. It can run a Turing machine file, and it can also compile Daedalus to a Turing machine. And if we think about the options that we have here, for any compile instruction, I would also like to be able to define where the source file is and where I want the output file to be. So maybe we have an option here for, this is a source path, And this will have the name of the file. And the output file for now, we'll just have it be hard-coded to be the name of the source path file. Then we have output path. And there's not really any flags for lexing WB1, so this is pretty much what it's going to be like. And then for WB1 to TM, we obviously are going to have a source path and output path, like before. But when we go from WB1 to Turing machine, we have the ability to define what optimization level we want. So we have an optimization level flag. And similarly with this, we have a source path an output path, and an optimization level flag. And then for running a Turing machine, we obviously need the source path of the Turing machine. And we have a source path for the tape. So source path, tape. And then there's a couple options that I would like for running the Turing machine. Things like a step limit. Turing machines can often run for lots of steps, and it doesn't really do you any good if your Turing machine runs for 10 billion steps and you're just kind of locked into that. So it'd be good to be able to set a hard limit on how many steps you're willing to run the Turing machine. We'd also like a flag, probably for showing the steps, so that the tape of the Turing machine and where the head is at currently will print out onto the console as we do it. And I think that's probably it. I think that's good enough for now. It would be nice to be able to combine certain instructions. For example, being able to combine these, because these two both generate a Turing machine file. It'd be good to be able to run immediately after, but that's not necessarily a top priority. Anyone who's writing a script to compile their Turing machine code will be able to just simply put these two right after each other, and that'll be fine. It'll still run exactly as if they were combined. So, in the Turing programming section, we're going to add a new function that is bool interpret command line args. And it's just going to take in, just like main, into argc and character pointer args. And we're just going to pass in those variables. Go to command line args, just argc and args. So, the first thing that we need to do is separate out the command word, compile and run. So, if we get args1, and this is going to be a char pointer, so we need to cast it to a string, or rather create a string out of it, and test if that's equal to run or compile. And then if it's not, we'll just obviously write out an error. So error, invalid command. And then read back to them what their command was. And actually, save myself some time here. Starting with string command. And this is args1 because if you haven't worked with the command line much, args0 is taken up by the actual location of the executable file to run. And this will probably be useful later. So read the command back to them. So that if they're typing in the console, they can see clearly where they may have made a typo or just put a wrong instruction altogether. So now we have if command run and if command compile. So we need to separate it into those two cases, which should just be done with an else if, actually, now that I look at it. So let me go ahead and separate it out. Else if so if command equals run. So what can we say about a command that is asking us to run a Turing machine? It needs a source path. This is definite. It needs a source path tape, also definite. And it doesn't have to have these flags. So the first thing that we can do is test the number of arguments and check if it's at least 2. Because if it's not, we know for sure that they haven't given us sufficient information. That's one way we can do it. Another way is obviously to just go through argument by argument. But the problem with that is that we have to keep checking at each chance we get to see if there's the correct number of arguments, so that we're not accidentally accessing args outside of the bounds. So if we go ahead and check the arg count. So how many arguments are we expecting here? Well, there's 1 for the executable, there's 1 for the command, as we have here, and then there's 1 for the source. And Judas, can you go ahead and mute yourself?
Oh, sorry.
Thank you. So yeah, there's 1 for the executable, 1 for the command, and then there's 2 for the paths. So we're expecting at least 4 arguments. Otherwise, we're going to have to test how many arguments there are. So we know for certain, and actually I just realized he forgot to check if there was even an arg1 in the first place. So if argument count is greater than or equal to 2, that's the most important thing. Else, so if there's only 1 argument, we know that they didn't specify a command. So we can standard cout error, please specify a command. And this will, later on, I want this to tell you all the available commands. So to do, make this print all available commands with syntax. But for testing for right now, we're just going to keep it simple. And it'll have to be, a whole list of commands with syntax and strings, probably just some defined list of strings up top. So if the argument count is 3, that means that they likely specified obviously the exe, the run command, and a source path, but they didn't specify a tape. So they didn't specify a tape. Alternately, if it's args equals 2, it means they didn't specify a source path or a source path tape. So if we do, if argc is less than or equal to 3, we know for sure that they didn't put out a They didn't put out a source path for the file, the tape rather. So let's go ahead and standard cout. Well, actually, it doesn't really do us any good to say that you didn't specify both a source path or for the Turing machine or the tape. So let's just keep this simple and say if argc equals 2, just please specify a Turing machine or a source path. Specify a source path for the Turing machine. Once again, if you guys have any questions at any point, I am monitoring the chats. So if argc equals 2, else if argc equals 3. We're just going to tell them to specify a source path for the initial tape. Alright, so that's all the error handling done. Now, there is a tricky part of this, where if they, let's say that they did something like .xe run, and then they decided to put the step limit here, and then, show steps, then this will be interpreted as the source path, and this will be interpreted as a source path tape. So immediately we need to check the, while we may have the right number of arguments, we are going to need to make sure that they're not confusing the order of things, and that everything is still being done properly. And this is very easy to do, because these flags have a very distinct hyphen in front of them, so we can go ahead and check for that hyphen. So we know that there's 4 arguments, so it's safe to access these. So if argc 2, and then just get the first symbol, equals hyphen, or similarly argc3 rather, 0 is a hyphen. So if either of those are a hyphen, we can immediately say that it's not a valid path. Invalid path variable. And then go ahead and let's see, figure out which one to print back to them. args2 0. This is kind of hacky, but it'll have to do for now. args1, args2, args3, and then standard endo. So basically it just figures out which one is wrong, because it's only one of these two, and then prints it out back to them. And it only needs to really print one invalid variable at a time. There's no purpose in just overloading them with everything that they've done wrong, Let's see. So now we know that at the very least, these paths are potentially valid. So let's go ahead and create the machine. And I realize Now this is probably going to need to be past a Turing machine to fill out. I know there are examples where it's just compiling that it's not going to be filling this machine out, but this is much simpler and breaking things up. So we have the machine, and we can go ahead and do machine.load, and then pass in args2, and the syntax of that will be taken care of by the load function, so we don't need to check anything on that, but we do need to check if it was successful. So if machine load equals 0, which is a success, now we don't need to put out an error because the machine.load function will already put out an error telling them let's see, this should be return -1. I haven't been putting those in. What was I saying? So yeah, all the error handling and error messages will be handled by the load function. We just need to check if this is valid. So if it is, then we can go ahead and load the tape. Otherwise, it's just going to return -1 itself. So if it successfully loaded it, now we need to try and load the tape using the third argument. And again, if it's equal to 0, then it was successful, and we need to go ahead and if machine load is 0. If it was successful, then we can go ahead. Otherwise, we just return -1. And again, we don't need to throw an error message because the load tape function will do that for us. Although right now there really isn't a way for the load tape function to fail unless the file doesn't exist. So we've loaded the machine, we've loaded the tape, and we're all ready to start running. What we can do from here is actually get ready to run the machine. And so if we look at now what our variables were, we had a step limit and we had a show steps flag. So we're going to need to find out if those were given. And so the syntax for the step limit is very simple. It's just going to be a hyphen with numbers, and the show steps is just a hyphen with a capital S. And luckily, by having one be defined as a number and the other being defined as a capital letter, we can keep them separate so that you can include one or the other, and we can very easily interpret which one you mean. And it also means you can do it in any order you want. So the flags are totally interchangeable. You can do any combination of them, and that's what we want. We want that versatility. So the first thing that we need to do is we need to check whether or not we actually have any flags in the first place. And we can do that by checking the argument count. So argument count is greater than or equal to 5. And remember, for 5, that'll be 1 for the executable, 1 for the run, and then 2 for the path, so that's 4 right there. And then greater than or equal to 5 will indicate that we have a flag. Of course, we'll need to determine whether or not the flags are valid in the first place. So if argument count is greater than or equal to 5, we know we have something after the source paths, and we also know that the source paths are valid. So if argc is greater than or equal to 5, then we can see. first we need to check if we have two or we only have one. So if argc equals 6, that means we have two flags. And what we'll need to do is determine whether or not those args are valid, rather that they are flags. And that's actually the same logic that we used up here with different numbers. So if the fourth argument, or rather the fifth argument, and the sixth argument both have hyphens, we know that they're both flags. And so now we need to interpret the rest of the arguments as their corresponding flags. So the first thing that we need to check is one of those followed by a capital S? Again, it's the same logic, but now we're let's see. We have to make sure that there's something even following the args. Let's see. If args for, because we can't just check if args for 1, because that's not guaranteed to be valid. I don't know if there's any way that we can get the size of the args because they are because they're args, they're carry double pointers. Let's see. So we know that we have flags in the first place. So what we can do is I'm not really sure how to make sure that we have the ability to access the arguments like this. I would think that we'd be able to, because it's not like we have argc here. I guess probably what we'll have to do is just compare the string itself and just say if args for equals, well, that's a pointer. It doesn't help to just dereference it. If we construct a string from it, standard string args4, and then we compare that to this, and then do the same for args5. Because if we have two optional flags going, then we know for a fact that one of them has to be this show steps flag. Because if it's not, then it's just garbage. It's not a well, it's either a step limit flag or it's neither, which is not a valid flag. So we know that one of these statements has to be true if they're valid flags. And then so else we just want to standard cout invalid or error invalid flag. And we can use the same logic that we did here. You can use the same logic here to determine which one needs to be sent back to the user. Just standard string args4, and this is, it'll get optimized away. So we'll just write it like that for now. args5. Right, and then endl. Okay, then that's looking pretty good so far. So if one of them is the show steps flag, we also want to get the other one. So we're gonna have standard string step limit be exactly the one that isn't this flag. We can just swap these around. And so this will give us back the supposed step limit flag. And we can actually test if this is a valid flag because we can do standard is not standard. Standard string, no, it's step limit dot is num, I believe. I'm trying to remember what the string check for is number. Check if string is number. So all we have to do is check if a certain substring is obviously you just have to check if after the hyphen it's a number, and then we know it's a valid step limit. So I believe, let's see, I think it's trying to remember the function. I could just do string to int, but I think I'll use a simple isNum function. This is one that I use once in a while, just to check if a string is a number. We'll probably separate this out into some sort of utility file. And isDigit is, remember, isDigit is from string. Which one is isDigit from? I believe it's from standard lib or C type. Maybe it's standard lib. No, I think it's C type. No, what is it from? Standard IO, maybe? It's weird. I'm not sure why it's, I thought it was standard lib that has isDigit. Is it not? Oop. Yeah, that's really weird. I could have sworn it was standard lib that has that. digit. Maybe it's standard C string or C. Maybe it's C type. It just didn't compile it. No? Is digit. Sorry about this. Is digit. Weird. I'll just have to write it in myself. Return not is digit. Oh. There we go. Guess it wasn't in the standard. I figured as C type, is that still good? Yeah. Okay. So now we just need to check is number step limit dot substring offset at 1, and then standard step limit dot size -1, right? Yeah. So this just eliminates that. So if it is a number, we know that things are valid. Let me see my print here. Yeah. If it's not a number, then it's an invalid flag, and we need to send it back to the user. Invalid flag, and it's just going to be step limit. And we should actually specify invalid step limit flag. So print the step limit back to them, and then no. Okay, so if it is a number, that means that we have all completely valid flags, and we have both flags. That's important. And so now we can run it in the loop. For now, it should be abstracted to a function, but for now I'm just going to keep it written out here. So we're going to have an unsigned int for the steps. Initialize it to 0. And then while steps is less than standard string to int step limit, and I'm just gonna go ahead and pull that step limit out, so change this to step limit string. And we're gonna have an unsigned int step limit equals standard s to I step limit string dot substring 1 to step limit string dot size -1. So while the steps are less than the step limit, and we know that this is safe to do because we already checked to make sure it was a number. So while steps are less than step limit, and the reason that I'm using a while instead of a for is that steps might need to be used outside of this later on. We'll just have to make sure to increment in here. So steps machine.step, and what I'm gonna do is, because we're gonna I do have a small error in here where I'm checking to see if I extend the tape and then moving. I'm going to actually swap this around so that I move and then extend the tape appropriately. That way the head is always at a valid location. Okay, and then machine.step, and then we want machine.print tape. That's going to be a new function that we're going to introduce. So entering machine.h, we're going to have void print tape. Let's go into Turing machine. Introduce Turing machine print tape. So now we have to think about formatting for this, because it's not going to be just as simple as iterating over the tape. Tape.size ++ s. So this just by itself, first off, we're going to want to build a string. So standard string tape, or tape string. Just initialize it. Tape string plus equals tape@s plus just a space, and then so that's actually a char. We need to convert that to a string. So standard string plus just a string space. So that'll just print out the tape nicely as, you know, something like that. But we also need to print the head, and that's a difficult thing with formatting it so that it looks like it's actually under the symbol that's beneath. So we're going to go ahead and print out or rather, we're going to create the string that's going to move the head, which is just going to be the caret symbol. So we also need the standard string head string, and again just initialize that. We can actually do this together. Head string. Actually, no, there should be two separate loops. For equals 0 s less than head dot position. Head string plus equals space, and then finally head string plus equals the caret. Okay, and then it's just as simple as standard cout tape string with a new line, and then head string. Okay, and so that will go through it and print the tape every step. And then also we need to check while steps less than step limit and machine.head .state. Oops, we're already in machine. And machine head .state. Or no, we need the machine head .state is not equal to A, which is the dedicated symbol for accepted. Actually, I have this here, so I'm just going to copy this. So, while we're less than the step limit, and this is true. Go ahead and run that. So now, when we exit out of this, either we've hit the step limit, or the machine has reached a rejection or acceptance state. So now if it is at a accept or rejection state, so if I'm going to print it out, if it is at an acceptance or rejection state, then we're going to print out accordingly if it's rejected or accepted the result. And then I think that'll be it, because it's printed it out every step, and then it prints out whether it rejects or accepts it. So yeah, so that's it for the case where we have both. Now we need to handle the case where we have only one or the other. And that actually involves breaking it down into two cases. So if flag. So we have if we have both arguments, and instead we need to go else. And here's kind of a weird choice. At this point we know that either argc is 5 or it's greater than 6. So we need to check, make sure that it is indeed 5. And then otherwise we just need to say too many options. We don't want there to be able to be just a bunch of garbage at the end of a script. So too many arguments. Standard L. So else if the argument count equals 5, then we can just simply check if one is the show flags, or rather show flag. So if it's a show flag, then we'll do that. Otherwise, we need to check if it's a number, which is what we have here. So else if is number and this is the step limit string. Instead, we're just gonna do standard string args4. And similarly here. Actually, we can go ahead and just standard string flag string equals standard string args4. Oops. Yeah, args4. And then there we can just compare flag string and else if is number flag string dot substring, and then accordingly flag string dot size. And let's see here. So if neither of these is the case, then we just have an invalid flag. Standard cout invalid flag. We can't specify what kind of flag it was that was invalid. It was just a wrong one. Flag string flag, yeah, standard, and okay, so if we just have the flag string, we can go ahead and copy our run code here. And it's not going to be checking for a step limit, it's just going to be running until it's done, if it is, that ever gets done. We don't have a step limit, and we don't really need to keep track of the steps. But we are going to be printing the tape. Conversely, if we have this, we still have the step limit. And here we know that this is just going to be the flag string. And it's just going to run, but it's not going to print the tape out. And then it's just going to result. So that's the entire run command done. And if we wanted to, we could test it out. I want to check and make sure everything is good here. But we actually don't need. Let's see. Making sure I call machine load. I do. Okay. I have a typo there. That should be machine load tape, or load rather, 1 and 2. I realize these are all off by 1. Is that right? Let's see. 0 is the exe, 1 is the command. Ah, yeah, no, that's right. So yeah, we can get rid of this. Or for now, I'm just going to comment it out. And we can go ahead and go into the project settings, and I can change it up to try and run a basic example. So if our command arguments are run, we need the source path, which is just going to be our regular input, which is what I just used for standard testing. And then the tape is going to be tape, or init tape. And then we're going to run it with, let's run it with both flags for now. And let's say only a step limit of 1,000. So I'm going to have it print the tape every time, and have a step limit of 1,000. So let's see how this works, if it does. Okay, so we step in. So argument count is indeed 6. So that'll take us right to here, which is where we expected it to be. It identified correctly that one of them was a number and the other one was a show string. And now it's simply going to run. And I'm going to go ahead and run it now. And I know you couldn't see that, but it did indeed run on the, let me see if I can get that up on the stream. So I don't know how well you can see that, but in the bottom right is the console output. And indeed, we can see all the symbols that we had written before, and indeed the Turing machine is moving left or right. And it moves really fast, obviously faster than one could really see, but if you have a Turing machine that's running a lot of steps, eventually you're going to be able to catch on to more or less what it's doing. And that's the important part. It's just making sure that everything is running appropriately. Alright, so the run works fine. Let's just test it with its with only one flag. So just with the step limit flag. Make sure that runs. And it does. Try and make sure it actually ends up in the right place as well. So yeah, it does. And then let's run it just with the show tape flag. And make sure that it ends up show tape flag right here. And it does. And now you can see what it did, print all that out. So we have the basics of our run command done. Obviously, it will need to be cleaned up eventually, but that's it's good for now. Let's see. So the compile arguments are going to be a little different. Because we have three options for what the compile is, we actually need an argument in between here that indicates which conversion we're doing. And I would like that to be an option beforehand. Not really sure how to do a syntax for that. I don't really want it to look like this. It's kind of hacky and unnecessary. Thinking it could just be something as simple as separating it. Maybe have two arguments, DDLS to WB1 or WB1 to TM. I think we could just do something like that. So have a compile input file type, output file type, the source path, the output path, and then obviously the optimization level flag. So let's see. In our Turing programming, we're going to be, let's see, this is the check here for if command run. We already checked, make sure that there's a valid, here it is, else if command equals compile. So from here, we need to get an input file type and an output file type, and make sure that they are valid. So we need to check and make sure right away that the arg count is good. If arg count equals, so what's the least amount of arguments that it can have to be valid? Well, there's only one optional flag. So we have the compile. Obviously, we have the exe, so that's 2, 3, 4, 5, and 6. So with 6 arguments or more, we know that the compile command has the potential to be valid. And we already tested that the command is compile, so now we just need to test for the source file type. So we have standard string source file type string, and that's just going to be args2 And then we have standard string output file type string, which is just args3. Okay, and so we're just going to test to make sure that these are valid. If source type file string equals DDLS or WB1, so it can only be one of those two. And likewise, the output file type string is equal to WB1 or it's equal to TM. And then finally, we just need to check to make sure they're not equal, because it doesn't make sense that your source file is a WB1 and your output is a WB1. That's not an operation. So, and source is not equal to output. So if that's the case, then we know that these commands are valid. They're doing a valid operation. And now we just need to get the source paths and the output paths. And we can do that just as simply as trying to open the machine that we got here. So if machine, or I'm sorry, so now we actually need to decide based on what our input file is. So if source file type string is Daedalus, then obviously it needs to be lexed. So we're going to lex WB1, and it's going to take in args4, which is the source path. And if we go to lex WB1, we see that it'll automatically output these let's see. Well, actually, this does raise a good point. For now, I'm actually not going to do an output path option because I want the output file to be the same name as the input file, but with the different endings. So if your input file is unary addition.daedalus, I want the output file to be unary addition.wb1 or .tm. And that's just temporary. It's just going to make things a lot easier. And that's what we see currently. So, in actuality, this needs to be 5. And we're just going to lex WB1, that one. And that needs to be done whether or not the output file source is WB1 or TM, which are the two options. But if it is TM, then we need to also do WB1 to TM, passing in args4. And this is part of why I want it to be the same, is that it just makes this a lot easier. And then it needs an optimization level. So now we also need to get the optimization level. And the syntax for the optimization I'm just going to take from regular compilers and just have it be tag 03, or in my case it'll be 00 or 102. but it'll default to no no optimization rather. So if output file string equals tm, that means that there's the potential to have the optimization flag. So we're going to check for the optimization flag. If we'll have an int optimization level, and it's going to be set to 0 to start. If standard string, rather we need to check actually if the argument count is right. If arg count equals 6, and that means they've specified an optimization flag. 1, 2, 3, 4, 5, 6 is the optimization flag. So if arg count equals 6 and arg's 5, I'm going to convert that to a string, standard string, arg's 5, is equal to string tag O 0. And actually, this is kind of cheating, but we really only need to check if it's O1 or O2 because we've already established it as 0 being the default. Well, actually, no, we need to check if it's valid because we need to send an invalid flag otherwise. So or is O1, is O2, and actually this needs to be a separate if check because we need to throw an invalid flag. So if arg count equals 6, and if it's a valid flag, we do this. Otherwise, we have to throw the invalid flag statement. So else, oops. There we go. And then I forgot to parentheses on this. If I think I'm missing a parenthesis, possibly. No, I have too many. There we go. So if it's valid, if it's not valid, we have to throw an invalid flag. Error invalid flag. And that's actually standard string flag string equals args 5. Flag string. Oops. And similarly here, flag string. Output flag string and L. Okay, so if we do have a valid flag string, then we just need to set optimization level equal to s to I flag string dot substring from 2, and it's just going to be 1 to get the number here. Okay, and then we can pass that in as the optimization level. And since I have an error here, it's weird. Do I have a missing parenthesis? Oh, here we are. Yeah. That should be in there. Yeah. Okay, and that should be it. I believe that takes care of all of our compilation. So let's go ahead and try and do some compilation here. So let's compile the input, and let me go ahead and load up the input files. I'll do that in a second. Input, and we're going to do it with optimization level, and currently the optimization levels aren't fully implemented. I just have O1 and O2 done because I overwrote O0 when I wrote O1. I wasn't expecting to have full optimization capacity, but I realized I needed it for debugging. So for right now, let's just do O1. Okay, so we're going to compile input with O1. And let me load the files into here. So we have input, which is, oh, and we didn't specify what kind we're doing. We're going to be doing compile. Let's do Daedalus to TM. So just do a full compilation. And so here's the input file. Let me drag and drop that. Here's the input file. And this is the unary multiplication code that I just added. And we're going to be compiling it into this. So just to make sure it does something, I'm going to actually erase this file. And then the end result of the Turing machine is going to be this, but unoptimized. So let's go ahead and hop into here. Okay, it's going to interpret our command line. Oh, what happened here? One second. Let me fix that. There we go, that's weird. Don't know how that ended up all misformatted. Let's try that again. Okay, so we hop into this function, and it should test command. Indeed it does. Sees that we have compile, we have enough arguments, it's a valid file conversion, and if... Oh, I just realized we never did WB1 to TM. I'll have to go back and fix that. So it's going to lex the file. So one of these has been changed, and indeed we see now the WB1 is done. The TM, however, is still unchanged. If the output file type string is TM, which it is, sets the optimization level, recognizes that we have an optimization flag, determines what that flag is, sets the optimization level, and indeed it does find that it's 1, and then compiles it. And we reload here, and we see that now it's unoptimized. Well, it's optimized at level 1. And so that ran just fine. Did everything perfectly. So we just need to fix the WB1. So if source file string, this should actually be else if source file type string is WB1, then we know that the output file string is TM. We just need to get the optimization level, which looks exactly like this that it is before. Can you go ahead and mute yourself? One second. Can you mute yourself? Okay, so we've got the optimization level. Just all that we did WB1. So yeah, this is the exact same as what we want to do. And this will be pulled out into functions, obviously. I just have it explicit for testing purposes. Okay, so let's go ahead and try out WB1 to TM. So we want a WB1 to TM, and let's do it on full optimization so that we can actually see a difference being done. So let's go ahead and hop to here, and hopefully it'll reach that. Okay, so it does. Goes through, finds the optimization level, recognizes that it's 2, and does WB1 to TM. And if I run that, I should get a statement that it's been done. And as you can see, it's optimized now. Okay, so I think this is all done now. And that's what we wanted, is we wanted a way that we can compile and run separately, change the optimization level, and all that. So I think that's the biggest things of what we wanted to accomplish today. Overall, I think that obviously we'll need to go back here and refactor things. It's pretty wordy. So. But it's just wordy right now for the sake of being clear. But yeah, I think that's a good starting point for adding the versatility to the file and all the command line logic. So I think that'll be it for today. Thank you to everyone who showed up for the stream and followed along with me. I know it was kind of boring at parts. This really isn't a visually stimulating project for the most part, but I think that once we get towards the end and we start doing a little more higher level stuff, it'll be a lot more fun to watch. So yeah, if you want to use this, try the language out for yourself, there's a link on my Twitch account to my GitHub, and specifically this project. It has documentation on there that kind of goes over what I went over today before I started coding. And if you have any trouble with using it, go ahead and open up an issue on the GitHub. And these changes that we made today should be out by the end of the day. I'm going to go over them somewhat quickly today before actually pushing. So yeah, thank you to everyone who came out and had a really good first stream. And hope to see you guys back again next time. See you later.